I want to thank the department for giving me the opportunity to speak to you all today. It's always great to give a talk on home soil. And this is a special talk because it's going to feature the world public premiere of a new exciting result in dark matter physics. Before I get to that, I want to explain why we need dark matter and then why I care so much about bounding this particular scenario of dark matter and why you should too. So there are a variety of experimental anomalies in physical systems starting around the galactic scale and larger that can't be explained by the known physics of the standard model of particle physics combined with general relativity. So if we work our way up in distance scale, starting at the galactic scale, through a series of groundbreaking observations spearheaded by Vera Rubin starting in the 1970s, this interesting property was observed. The stars in these galaxies are moving much faster than you would have predicted if the gravitational well was being sourced by visible matter alone. So already right here, we have a clue that there is some large component of the universe that's massive, it's gravitating, and it doesn't interact with photons, with light. I think there's an even more visceral demonstration of the need for something like dark matter if you go out to the galactic cluster scale. And of particular interest is the bullet cluster, which is actually two clusters that collided once upon a time. And most of the visible matter in these clusters, somewhat surprisingly, is not in their stars, but in the interstellar dust. So as these clusters passed through each other, the dust interacted with itself. There was a great deal of friction. It warmed up. It's glowing in the X-ray. That's what we see in these colors on the figure. So the colors are showing us where the visible matter is. Through gravitational lensing, we see that the gravitational wells are located far, far away. Expanding out to the largest possible physical system we can study, the entire universe, as we probe experimentally through the cosmic microwave background. These are the remnant photons left over from the hot primordial plasma that was around after the Big Bang, and studying their fluctuations in temperature at a variety of length scales, we see compelling evidence, again, for a massive piece of energy that does not couple strongly to photons. And the advantage of these CMB measurements is we can actually quantify the amount of the universe contained in this missing matter. And the number comes out to be a rather shocking 27%. By contrast, the baryons that dominate your and my mass, the everyday standard model matter, constitutes something closer to 4%. So just in terms of demographics, dark matter wins by a substantial fraction. And so if you knew a lot of physics, but you didn't actually know what physicists worked on today in research, and you were presented with this slate of anomalies, I would contend you would naturally be drawn to three possible explanations. Okay? The first is you might think, if all of this interesting physics is going on at very long distance scales, maybe there's something we just don't understand about gravity. Maybe we need to modify GR, maybe even modify Newtonian gravity in a way that wouldn't show up in everyday systems like here on Earth or even at the scale of the solar system, but maybe at very long distances, you get something like that to explain some of these effects. And this is actually somewhat successful in explaining this galactic rotation curve problem. The difficulty with this approach is that it fails at almost every other anomaly that dark matter is needed for. And in particular, for something like the bullet cluster, how could you have the matter here and have the gravitational well be something like 10 Milky Way galaxy lengths away? I don't know of any serious attempt to write a theory that would have thing here, gravity that far away. So I think as an explanation of all of these anomalies, modified gravity is dead. Another thing that you would conjecture is that maybe dark matter is black holes. Now, you could even imagine, right, your science literate but amateur neighbors saying, couldn't dark matter just be black holes? You're almost prompted linguistically to think that there is some connection between the two. This is a perfectly valid and interesting idea. The problem is we've been looking for this for decades now. And if you look in the mass regime where dark matter could be explained by black holes, at first pass, it's all ruled out. Now you can go back and litigate some of these bounds, maybe the attempts to find these black holes by looking at various lensing effects as these massive things move around our universe in great numbers. Maybe they can be relaxed a little bit, there's probably still some viable region right around 10 to the 15 kilograms. That's something like an asteroid mass black hole, which means this isn't a conventional, stellar collapse black hole. This is some exotic primordial thing from the early universe's cosmology. Somehow the universe would have had to make just the right number of these things, just at the right mass, and just at the right scale that someday humans would find it most difficult to probe. So that's still a logical possibility. I think there's still work to be done there, but it's not where I would place my bets. And so I'm going to move on to the third candidate explanation, which is that dark matter is something like a neutrino. And by that, I mean it's an elementary or near elementary particle. It's necessarily neutral because we know it doesn't couple strongly to photons. But even making that rather strong assumption still leaves you with a very large parameter space, something like 50 orders of magnitude in mass if you want dark matter to explain the physics of the smallest scales where it's been observed out of dwarf galaxies. And so you can't, much as one might want to, go out and do a dedicated experiment and search all 50 orders of magnitude at once. Now you need to make an even stronger assumption if you want to go look for something like dark matter. And what I'm going to be focusing on today, what I contend is some of the more neutrino-like examples of particle dark matter are the so-called weakly interacting massive particles, or WIMPs. Their natural scale is around a TeV. And at the end of the talk, time permitting, I'll explain how this idea might be generalizable to much higher energies. Before I get into the physics of WIMPs, let me say a little bit about the particles that inspire them. Neutrinos, after all, are a kind of dark matter. Okay? They're very feebly interacting, they're prolific, they're neutral. And kind of remarkably, up to order 1 factors, depending on your angular orientation, at this moment, through every square centimeter of your body, every second, there are 65 billion neutrinos passing through you, right? So we can all just sit here a moment, right, and enjoy this ambient bath of neutrinos. By contrast, something like WIMP dark matter at the weak scale, there need to be about 1 per every 2 liter volume, right? So the known physics, I would say, is actually much more exotic and almost hard to believe than the speculative physics. Now you might think, oh, if neutrinos are a kind of dark matter, could they be this thing that we're after? And that's wrong for a couple of reasons. First of all, we've measured the amount of neutrinos in our universe, and it's something like 1 part in 1,000. Right? So we're trying to get to 27%. So there just aren't enough of them. There's also a very important property that neutrinos have that keep them from being this dark matter, which is that they're extremely light. It's only in my lifetime it was established that neutrinos have mass at all. And so in the early universe, they were this very, very fast-moving, hot relativistic plasma. They couldn't do one of the main things we want dark matter to do, which is form gravitational overdensities, which turn into deep gravitational wells, which eventually see the structures of galaxies become you and me, et cetera. So in detail, it can't be the standard model neutrinos, but it could be something a lot like them, but just a bit heavier. That's what I'm going to take as my conservative assumption. It's important to note, and this will come up throughout this talk, that even though neutrinos are electrically neutral, they still participate in the electroweak interaction. This is the SU2 gauge symmetry of the standard model. That's something we can exploit to explain the physics of dark matter. So returning to WIMPs, why do they make such a compelling candidate, besides just the sort of existence proof that we can have lots of things that we can't readily see, like neutrinos? Well, after the hot Big Bang, or in a more modern understanding, the period of reheating after inflation, there was this very hot primordial plasma. It sustained particles whose masses were at or below its temperature. And so throughout this physics, you had particles annihilating. And as long as the temperature was heavier than that particle's mass, this annihilation process could run the other way. But as the universe expands and cools, eventually you'll drop below the mass of some heavy particle. And then this process starts running only one direction, right? So we'll take chi here to be our dark matter. It annihilates just this psi particle, whatever that is. Psi equilibrates at this colder temperature, and it can't reform chi. So we start destroying the dark matter. This process continues for a while, but eventually the universe expands so much that this plasma is so cold and so diffuse that these dark matter particles can no longer find one another to annihilate. And so whatever is left of them sticks around. Of course, it's also important that they carry some sort of conserved charge. They just don't decay. But we have plenty of examples of conserved charges in nature, and it's not hard to assign one to the dark matter. So on this figure on the right, I have a quantification of that cartoon universe history I just went through. Now, it's important to note that there are two notions of density one keeps track of in cosmology. So there's the sort of naive density, just what is the energy per unit volume? That is denoted by omega. And then there's the so-called co-moving density, right? The universe is always expanding. So if I take a set of dark matter particles and I just let the universe expand, well, then their naive density, of course, dilutes because that space-time expands. But if I haven't destroyed or created any of them, then we can say their co-moving density is a constant because their density is just diluted with the expansion of space-time. And that's what's being plotted in this right-hand figure. So the x-axis here is mass over temperature. As the universe cools, right, this ratio is going to get larger. So starting when the temperature drops below the particle mass, they start being annihilated. And this process proceeds until the universe gets so dilute, they can't find each other to annihilate at any great rate anymore, and they've frozen out. So this sometimes is called a thermal relic, right? The universe was hot, some particle species that was stable froze out of it. We can check some basic things about the scaling. If we increase their annihilation rate, well, we deplete the dark matter density more. Okay, that checks out. We can also see that in this expression for the energy density contained in dark matter. It scales inversely with the annihilation rate. And then what's very interesting for particle physicists is that there are two dimensional scales that enter this quick estimate. One is the current temperature of the cosmic microwave background. If you want, this is just sort of normalizing the clock on the cosmic history we're putting in to get this present dark matter density. The other, since we're doing cosmology and necessarily involving gravity, is M Planck, which is controlling the strength of the gravitational interaction. And even though these are gravitational cosmological parameters, their geometric mean comes out to be a TeV. This is suggestive to particle physicists because a TeV is sitting right over our heads, right? This is the energy scale being probed by the LHC. This is the scale of electroweak physics. So this gives us some hope that dark matter does something other than interact with us gravitationally. It may have some connection to the standard model because on very general grounds, we're getting out a standard model scale. If we plug in a schematic cross-section, we can even get an estimate for the dark matter mass, which again is coming out to be somewhere around a TeV. And so dark matter really can just be a heavy neutrino. We can essentially take the known particles and forces that we have and to explain all of these experimental anomalies, augment the standard model by some simple state. So it could be that in this annihilation process, we already know the identity of every particle in it other than the dark matter itself. Okay, so what it's annihilating to could be standard model particles. The interaction that's mediating its annihilation could be one of the standard model interactions. And so this allows us to write down a specific concrete model for what dark matter can be. We take it to be a heavy copy of the neutrino in the sense that it is charged under the electroweak gauge group. It participates in the electroweak interaction, and it has necessarily an electrically neutral component. And even if you don't spend a lot of time working on electroweak physics per se, right, the mathematics here is very familiar. It's the same SG2 group we're used to encountering with spin and quantum mechanics. So sometimes this group is called isospin. And just like you're used to spin doublets, triplets, you can have isospin doublets, triplets. And this is how we quantify the particle that we're adding to the standard model. So I would say it's a very conservative addition to physics to explain dark matter, to say it's some probably low dimensional representation of SU2, some new particle charged under the electroweak interaction. Okay? And some of the lowest dimensional representations we can look at are, say, doublets, triplets, and quintuplets. And once you say dark matter, it transforms under this representation. It has these weak charges, these electric charges. We know all of its interactions. And then if you want it to realize this simple thermal relic scenario, that uniquely fixes the mass of the particle. So there are certain very special mass values we care about for each of these representations. So if it's something like an electroweak triplet, it can realize this simple story, be all of the dark matter at 3 TeV. If it's a little bit lighter than 3 TeV, it can still make up some of the dark matter, but then you're on the hook for explaining what else is there. It could be heavier than 3 TeV, but then it would be realizing some more non-trivial cosmology. It couldn't just be a simple thermal relic. And what's exciting, right, is these scales are not far away, right? These are scales that we are testing today. And I have a new result about the physics of this today. You can, of course, take this idea to its logical extreme. You could ask, how big of a representation of SU2 could I add? You can get up to about 15 before the quantum field theory breaks down. Now, all of the matter we've observed so far charged under the electroweak gauge group is in the form of doublets or singlets. So it'd be a little perverse if nature all of a sudden skipped to 11 to be dark matter. But we have to acknowledge that as a phenomenologically and logically viable possibility. So we are now getting toward something we can go out and test with a dedicated experiment. And we're going to exploit this same annihilation property of the dark matter that seeded its relic abundance to begin with. In the early universe, it was annihilating very rapidly. There's a faint echo of this annihilation that's still going on today, wherever you might find a great deal of dark matter. Since we've coupled it to the standard model, it can produce standard model particles. And my particular interest is when it produces photons, right? Somewhat ironically, even though it doesn't couple directly to photons, you can pick up the photons as an experimental signature through this annihilation. These are TeV or larger scale photons, which means when they slam into the atmosphere, they create this flash of Cherenkov radiation. They're moving faster than the speed of light and air. You get something like the optical equivalent of a sonic boom. Kind of amusingly, the light that comes out of the Cherenkov flash is in the optical range, but its duration is only a few nanoseconds. So you can't actually go out and look for them with your naked eye, but they can be picked up by sensitive telescopes. And there are a variety of interesting gamma ray signals purely in astrophysics. So things like supernova remnants, the active galactic nuclei, pulsar wind nebulas. There's been a rich gamma ray program in astronomy since the 1980s. And so one of the things I like about the indirect detection program for dark matter is that there's all sorts of interesting non-trivial astrophysics you can do with the same experiment. You're not just buying a lottery ticket and hoping that you discover dark matter. And if you don't, that's all you have to say for your experiment. There are 3 currently operating telescopes in the world that utilize this effect. Rich already mentioned Veritas, which is the one I'm a member of. And there's a successor experiment currently under construction, about which I'll have more to say later. So here is my favorite of the Air-Cherenkov telescopes, Veritas. It's located between Tucson and Nogales. They have a nice visitor center. It's in a beautiful location. I recommend it as a day trip to visit this 3-of-a-kind scientific instrument in the world that is not so far away. I've shown on this map some of the other significant astroparticle experiments. So the other 2 Air-Cherenkov telescopes, HESS is in Namibia, MAGIC is in the Canary Islands. And together, these are all working to discover dark matter through this indirect detection program. And of particular interest to us with Veritas is that it has taken a large data set looking at dwarf spheroidal galaxies, which, as I'll explain, are a promising dark matter target. So we can put this all together now into a practical experimental program. So we've understood the physics of dark matter annihilation. We've understood the physics of Cherenkov light coming from TeV photons. So what do we do? Well, you take your telescope and you point it at a place where you expect there to be a lot of dark matter. And the advantage of using photons is that they travel in almost straight line trajectories in our local astrophysical neighborhood, although in principle, you could do indirect detection with any light, stable standard model particle. One place that naturally suggests itself for testing dark matter is the Milky Way galactic center. Okay? It's a huge gravitational well. It's relatively nearby. And I'll have some things to say about limits one can make on dark matter with the Milky Way galactic center, but there are challenges there. One particular challenge is that there's a lot of non-dark matter physics in the galactic center. It's very baryon dominated in the inner galaxy. There are a lot of non-trivial, non-isotropic backgrounds one needs to handle. Additionally, that baryonic physics in the galactic center makes it difficult to quantify just how much dark matter you should expect to be in the galactic center. And so here is some dark matter limits from the magic experiment, and there's something like a 2 order of magnitude uncertainty based on our ignorance of the detailed distribution of dark matter in the galactic center. But we can take that as it is and fold it into our systematic uncertainty and see what we can achieve nonetheless. Why is there this uncertainty? Well, we know that there should be a larger concentration of dark matter toward the galactic center. But as a cartoon statement, we don't really know if that distribution is shaped more like this blue cuspy curve or this pink flatter chord curve. So the way I like to quantify this uncertainty is to say, when you place a limit on dark matter, what core in your dark matter distribution have you assumed? It's not hard to imagine that if I square and integrate these functions, I could come up with things like a factor of 100. We don't know that much about the distribution of dark matter in the inner galaxy, but we do know something, right? If you make that core too big, you can't properly explain, right? The famous galactic rotation curves, et cetera. We're out at 8.5 kiloparsecs here in the solar system. There's not evidence for a core at our scale. You can make a core about as big as 2 kiloparsecs and still be consistent with observation. So that's a handle you have for doing the indirect detection of dark matter with the inner galaxy. But the other approach one can do is to sidestep the inner galaxy entirely and look at a different set of targets, as I mentioned, Veritas does with the dwarf spheroidal galaxies. So these are interesting astrophysical systems. Here's a map of our nearby neighborhood. So this gray blob in the middle is us in the Milky Way. And there are these small galaxies that are very dark matter dominated. We believe they're very dark matter dominated, both because of you need the same dark matter distribution to explain their stars' rotation curves. And also they have enormous mass to light ratios, a couple orders of magnitude, at least larger than the mass to light ratio in the Milky Way, where there is also a non-trivial amount of dark matter. An exciting thing about these targets is this is a relatively new branch of astrophysics. Many of the dwarfs in this slide were discovered this century. And there are still dwarfs being discovered. And I'll have something to say at the end of the talk about a new potentially exciting dwarf that would be very exciting for dark matter limits. And so these dwarf spheroidal galaxies are almost an ideal system for indirect detection because they are basically made up of dark matter and stars. So you don't have to worry about other non-trivial gamma ray backgrounds, and you have stars there to trace out the distribution of dark matter that they contain. So what does one do in an indirect detection experiment? Well, you're observing some flux of photons, and it's worth saying something about where that flux comes from. Okay? So part of it, which I've highlighted in blue, is the sort of pure particle physics or pure quantum field theoretic calculation. You just want to know if I have these particles in my theory and I let them interact, what is their annihilation rate? Okay? So that's something theorists can go and compute as well as they can. But also affecting the number of photons you see in your experiment is, well, the size of the region you're observing. That's something you have total control over. But you also are reliant on knowing how much dark matter you're looking through, right? You could have, this could be an enormous rate, but if you're looking at a patch of empty sky where there's no large gravitational well out there, that J factor that is going to be very small because the dark matter density in that region is going to be very small. But if you're looking at a region where you expect there to be a lot of dark matter, okay, then rho could be large to give you a nice observable signal, but now you're on the hook for quantifying it, right? Because it's directly entering your calculation. This is what is difficult to get a handle on in the Milky Way. It is easier to determine with dwarf galaxies. So here is from the paper that we use for our Veritas J factors. The J factors of various dwarf galaxies, we see that there can still be some large uncertainties in some systems, but for the most part, we are doing better than a 2 order of magnitude uncertainty. You obtain these J factors by measuring the velocities and radiance of the stars in these dwarfs. You plug this into a Jeans equation, which tells you how a distribution of particles behaves in the presence of a potential. So you can determine what that gravitational potential is in these dwarfs that's coming from stars plus dark matter. You've measured the stars. So what's left is the dark matter, and you can get a handle on rho squared and thus your J factor. Oh, and by the way, it's rho squared because we're annihilating dark matter. So with this indirect detection program. Now that we've understood it, I want to say we can go about it a couple different ways. Okay? So the first is the one I've mostly been discussing so far, that we just add a new particle to the standard model. This is some electroweak WIMP. This is a specific model. We can do very precise calculations and go to it. At the same time, right, you could also just take a bottom-up approach and say, I don't have a complete theory for what dark matter could be, but as long as it's annihilating the standard model particles, and if it's doing so at sufficiently high energy, somewhere down the line, something is going to radiate a photon, and I could just look for excesses of photons if I point my telescope at a dwarf galaxy versus pointing it at some uninteresting piece of the sky. Okay? And even though we're talking about physics at scales starting around the LHC scale to 1,000 times the LHC scale, right? These are tests, these are limits we can place today. So going back to the electroweak WIMP theory, why it takes non-trivial theoretical effort to study this particular model of dark matter. Well, it comes down to the fact that's all too familiar to us that you can have very simple equations. It's a very simple addition to the standard model, but simple equations often don't lead to simple solutions. If you want to solve for an observable, like the annihilation rate of these particles, typically we do this in quantum field theory and particle physics with Feynman diagrams. I've already shown a few. Feynman diagrams are very good for doing time-ordered perturbation theory. But the problem is many systems, including this one, contain non-perturbative effects. And so you need to go beyond simple Feynman diagrammatic analysis. In particular, there are 3 bits of non-perturbative physics that enter into electroweak WIMP annihilation. There is a long-range force that deforms their wave functions when they annihilate. The fact that you're destroying very massive particles and making very light particles sets up a shower of radiation that requires working to perturbation theory to all orders. And because this spectral shape comes out in the form of a line, there are some kinematic restrictions on that rate that further sort of numerically spoil perturbation theory and require you to treat with a non-perturbative technique. And as Rich previewed, the tool that we're going to use to make these statements is called effective field theory. So we were already doing quantum field theory by virtue of doing quantum relativistic physics. But we're going to apply the particular quantum field theory technique of effective field theory. So there's a nice analogy between effective field theory and digital signal processing. If we take the sort of usual quantum relativist equivalence of energy, mass, momentum, and frequency, right? So if we consider the once mighty compact disk, right, part of what gave it efficiency in information storage is that it exploited the fact that human hearing cuts off around 20 kilohertz. So you don't need to keep track of frequencies that high. You can get a reasonably sounding recording by getting rid of them. And on the quantum field theory side, if we're doing a low energy experiment, instead of that low energy experiment being your own hearing, being some sort of process, you don't need to keep track of all of the details of all of the higher energy, more massive particles in the theory. For something like a muon decay, we now know that the muon decay proceeds through a W boson. Right? But you don't need to include that as a propagating degree of freedom in your theory. All you care about is that this interaction vertex exists, and then you can explain why the muon is decaying to an electron and neutrinos without keeping track of all of the additional details that come in with having a propagating particle. Okay? So this is a very, I'd say, traditional approach to effective field theory. Right? If you have heavy particles in your theory, you can systematically remove them by doing the quantum path integral, integrating out their degrees of freedom, and you may have yet still some signature of their physics at low energies, and then you can improve it systematically. And eventually, if you get to a high enough energy, well, then you would need to account for that W boson. But just as we've moved beyond the compact disk, okay, and the digital signal processing side, there is a field known as psychoacoustics, which exploits even further properties of human hearing. The fact that you can't hear very soft, high-frequency sound on top of very loud, low-frequency sound lets you cut out other pieces of an audio sample and store it even more efficiently. Right? So an MP3 is about an order of magnitude more efficient than a compact disk, still leaving you with a reasonable audio recording. Similarly, on the effective field theory side, we can think not just about which particles are heavy and we can systematically remove. But what regions of momentum space where these fields inhabit do we or don't we get the dominant contributions to our observables? This is particularly important in the physics of showering the radiation of a lot of particles, which is very relevant to dark matter because that's what's going to happen as these heavy particles annihilate. So what you can do is, without removing whole particle degrees of freedom, you can carve out different momentum space regions in these quantum fields, dropping the ones whose contributions are subleading and keeping the ones whose contributions are dominant. So how does this work in radiation? Well, if I were to draw some Feynman diagrams corresponding to each of these internal virtual particles, there would be a propagator, 1 over the Lorentzian form momentum squared. And we see that there's a kinematic enhancement if what it's radiating is either very low energy, right? One of these energy factors going to 0, or very collinear, right? The split occurring at very narrow angle. So those parts of our momentum space are going to dominate the process that we observe. And there's a sort of traditional way at getting at that. If you have a calculation and you know where it's numerically dominated, you could draw a bunch of Feynman diagrams, then expand about what you know to be the leading limit, right? And then, toss whatever you think is higher order than you care to keep track of and deal with the rest. That's a calculational simplification, but it's also a bit inefficient, right? First, you had to do all the Feynman diagrams. What effective field theory lets you do is write down a new quantum field theory whose Feynman diagrams, if you want, come expanded up front. So you just draw the diagrams in that theory. They are only capturing that leading information. If you need to put in subleading contributions, you can put those in systematically. And so this effective field theory is efficient at getting at these radiation production through soft and collinear splitting, is appropriately enough known as soft collinear effective theory. It was originally developed in the start of the century to study processes in the strong nuclear force, or QCD. And almost 10 years ago to this month, my collaborators and I were the first to apply that theory to the annihilation of dark matter. How that affects your calculations? Well, as I said before, because you're subjecting these massive particles to enormous acceleration as you annihilate them, you're getting an almost classical-like radiation pattern. You can do a semi-classical calculation. In fact, the kernel of this additional exponential factor that modifies your cross-section in the presence of the shower of radiation, you can find a derivation of that in Jackson's E&M book. But you'd like to be able to get that from first principles quantum field theory. First of all, just because that's the theory we know to be correct at describing quantum relativistic physics, but also by getting it in an effective field theory, you can improve it systematically. And we see here that it's just not sufficient to do a simple Feynman diagram to get this exponential factor, right? Here's the perturbative coupling. Feynman diagrams work sort of alpha by alpha, right? You can draw more legs, put in more alphas. Okay? But this is an exponential. If you want that to get that factor, you've summed an infinite class of Feynman diagrams. And the effective field theory gives you a straightforward way to do that infinite sum. We can also see why the resummation is necessary if we just expand this to leading order n alpha and plug in the parameters for an electroweak WIMP. You're talking about something like a 60% correction, right? So there are order 1 factors at stake in whether or not we can predict our dark matter theory successfully. And as we'll see, right, getting these order 1 factors correct is essential for deciding whether or not a particular theory is viable. Another feature of the effective field theory is it allows you to Lego brick your calculation because you've split up your theory into different parts of momentum space. You can do different parts of this annihilation process independently. One particularly nice simplification that my collaborators and I found are that the soft and collinear pieces or jet pieces of the radiation are independent of the representation of SU2. So whether you're doing the triplet or the 11-plet, those very non-trivial functions to obtain, you just get to recycle them over and over. That's a result of the effective field theory. What we also see in this annihilation diagram is that there is non-trivial physics affecting how these particles annihilate. And that's due to the fact that we are now talking about particles that are so heavy, the electroweak interaction for them is actually a long-range force, right? For the muon, it was the opposite, right? The W was so heavy, we didn't need to keep track of it. We could just treat it as some infinitesimal distance point-like interaction. Here we're in the opposite regime. We're much, much heavier than the W, right? And the limit that we're infinitely heavier than the W, well, that's like saying the W is massless. That would just make it another Coulomb-like interaction. In the presence of this long-range force, the wave functions of the particles that we're annihilating, well, if it's an attractive force, they actually get pulled toward one another. And so one needs to solve the Schrödinger equation to determine what their wave function is in their annihilation region, which to good approximation is just their wave function at the origin. In traditional perturbative Feynman diagrams, that wave function factor is 1. In a system like TeV scale electroweak WIMPs, we see that that factor can be substantially larger. So you're making a mistake at the orders of magnitude level if you don't account for the long-range force. And if you're wondering about this resonance phenomenon in this so-called Sommerfeld factor, you get a resonance every time a new bound state enters the spectrum as you raise the WIMP mass relative to the W mass. Okay. So we can put this all together into a prediction for the annihilation rate of WIMPs to photons. This is from a 2018 paper my collaborators and I wrote for SU2 triplet annihilation. Some things to point out here. So first of all, we're differential in the energy fraction of the photon compared to the WIMP mass. In a simple 2-to-2 kinematic process, there is a monochromatic feature in the photons. They come out with energy equal to that of the WIMP mass. Okay? As an exercise, you can verify that that's the case if you take the WIMPs to be at rest. So I can't plot this function because it has a delta function in it, but I can convolve it with, say, some smearing due to the energy resolution of any realistic experiment. And you see the particle physicist's favorite thing in the whole world, a bump, right? And almost every background in astrophysics is smoothly varying. And this is, right, this is what particle physicists are trained to do since childhood, is to find bumps on smoothly varying backgrounds. And so now we're in a position to go out and actually test for these theories. Before I get to some of the tests, it's just worth noting that this is the effect of working to higher order in our expansion. We see nicely that the central value in the integrated annihilation rate hasn't changed very much, showing that we have good theoretical control. And also by working to higher order in our resummation, we are substantially reducing the theoretical uncertainty due to the unknown renormalization scale. So in 2018, with some Hess experimentalists, we recast a search from 2013 looking for electroweak WIMP dark matter. And naively, it seems like this thermoelectric neutrino is ruled out. But the catch here is that inasto actually means a very cuspy dark matter profile. And as I said before, actually, you can put in a substantial amount of coring in the distribution of dark matter in the galactic center and still remain consistent with astronomical observation. And so this result does not kill the Wino. We've proposed a very aggressive galactic center analysis that actually could require a core so large that you would close that halo loophole, but that analysis is yet to be done. In the quintuplet paper I wrote with collaborators last year, we did a similar projection. Again, Hess currently can't rule out quintuplet representation. Maybe it could almost do it with its full data set, and the successor telescope, CTA, will make a definitive statement about quintuplet dark matter. And just as an aside, it's worth noting that in the astroparticle community, there continues to be back and forth debate about whether or not there is a core of some size in the center of the Milky Way. So let's sidestep that debate for the moment and move back to the other target, dwarf spheroidal galaxies. So my colleague Connor made this nice plot for a meeting last summer where he showed the J factors of various dwarfs that Veritas has observed times the exposure. Right? Of course, you care about the total amount of data you've taken. It doesn't help if you have some dwarf with an enormous J factor if you never spend any time observing it. For statistics aficionados, I've put our maximum likelihood analysis on the right. But the crucial thing I want to emphasize here is that because we expect just an isotropic background of gamma rays contaminating these dwarf signals, we determine the background via a data-driven technique where you just point the telescope at essentially empty sky. You're taking so-called off-region data. You take those counts. Some of it is isotropic gamma rays. There's actually still a large background due to cosmic rays. In general, cosmic rays have different sort of morphology in the telescope compared to gamma rays, but you have so many more of them that even with rejection efficiencies at like 99%, that still gives you a large background contribution. So folding that all together, we can place our limit. Okay. So here it is. Here is the world premiere Veritas dwarf toroidal limit on we know dark matter. Okay. It's this blue line here. We can compare how we fare to our rivals at the other experiments. And you might say naively, it looks like we do a little bit worse. Okay. But this is where we can litigate the J factors. They are using an older, more aggressive set. We are using a newer, more conservative set. One could do the exercise to reweight their analysis by the up-to-date J's. I think the conservative statement here is that all of the experiments are coming in around the same sensitivity, which makes one wonder what we could achieve if we were to all join forces up at larger masses. So this wouldn't be a thermal relic we know. This would be a we know coming from some more exotic cosmology. You see that I don't have to litigate J factors like the lawyer. We are just doing unequivocally better. And principal reason for that is that, well, these calculations that my collaborators and I worked so hard to obtain, showing not just the monochromatic line of photons, but the detailed smeared continuum spectrum that trails behind it, we're making use of that. We're making use of that in a way that allows us to set a limit. You don't have to have a primary photon at, say, 30, at 100 TeV. If dark matter really is at 100 TeV, it will radiate so much lower energy photon that could still lead to an observable excess. And so next week, Veritas has deputized me to present these results at the TeV Particle Astrophysics Conference at the University of Chicago. This is a Veritas result, but this is the group of people that did this particular analysis. And I want to especially commend my ASU undergrad researcher, Olivia Kelserano, whose efforts were crucial in getting this result out here to you today. The punchline is that the thermal relic we know is still viable, right? But everyone is getting closer. So if it's there, it should be very nervous, or I guess awaiting its big discovery. Going forward into the future, the successor telescope to that triplet set of MAGIC, Hess, and Veritas is CTA. On a variety of parameters, it's going to do an order of magnitude better. It's simply a giant experiment. So Veritas has 4 telescopes. CTA South, the larger part, has over 100. Okay, CTA North has 19. It is going to either discover electroweak WIMP dark matter or utterly demolish the hypothesis, and that should be happening all in the next decade. And it's located in the Canary Islands and in the Atacama Desert of Chile. Some of the things it will do, I think it's fair to say that the dwarf spheroidal data is eventually going to rule out or discover the we know. But as far as other representations, there's a very motivated dark matter scenario, which you might wonder why I haven't said more about, which is dark matter being a doublet. Why did I start at the triplet when I could have started at the doublet? Actually, you need 2 doublets, because if you just had 1, that was ruled out in the 80s. It's not such a stretch to have 2. And then once you have 2, it's actually very hard to discover. But my frequent collaborator, Nick Rod, and some of his colleagues recently projected what CTA could do for Higgsino doublet dark matter in an all but the most pessimistic Milky Way dark matter distributions. CTA will be able to rule on it. I have work in progress with some collaborators now to look at these various electric representations, and we can get all the way up almost to the 11 with CTA. These are galactic center analyses, and rule them out, okay? So maybe there will be some set of electroweak WIMP diehards clinging to the 13 for the rest of the century, but that's where you would be forced to go. Now, while I think electroweak WIMPs are very motivated and very conservative and worth effort to search for and study, any model of beyond the standard model of physics is more likely to be wrong, is likely to not actually be what nature does. And with sort of Judgment Day coming on the scenario, a couple of years ago, I started thinking about what my next move would be with dark matter. And I think there is an interesting and only lightly explored case for dark matter to be something much heavier than the weak scale. Part of that motivation is because it's a natural thing to look for with indirect detection. Part of it is because we know there is interesting physics sitting over our heads at much larger scales. There's almost certainly something responsible at large scales for the physics of inflation. There is an enormous, at 10 to the 19 GeV, something out there that explains quantum gravity. So there are reasons to think that there are new particles waiting to be found at enormous energies. Part of why this corner of parameter space got neglected for a while was a sort of unintended consequence, I would say, of this paper by Gries and Kamienowski in the 1990s, where they took one of our most sacred principles in physics, the unitarity of quantum mechanics, and there is a result in quantum scattering that says that cross-sections can't be too large in order to be consistent with unitarity. And since we've determined the annihilation cross-section of dark matter in the early universe, right, that was a parameter that entered our expression for its current density. If you make the mass of dark matter too heavy, then there's a unitarity limit on how big that cross-section could be. And updating some of their numbers, you find that in order to be consistent with unitarity, dark matter needs to be lighter than about 200 TeV. But there's a big loophole to that bound, which actually was in Gries and Kamienowski's paper, but the lore that got repeated neglected their caveat, which is that this unitarity constraint only holds for each value of angular momentum. Okay, so J by J, you have to respect unitarity, or you've done something horrible to quantum mechanics. But if all you're trying to do is destroy dark matter, you don't care how many J's it takes, okay? 10, 100, right? All you care is that the dark matter is destroyed. And so J by J, you can satisfy unitarity, but if you sum them up, if you have a reason to sum over a large number of channels, you can get a much larger annihilation cross-section. In particular, if you do that sum up to something like the semi-classical angular momentum, something like, it goes like MVR, right? You replace the dimensions, the mass dimension that you had previously, thinking of your dark matter as a simple elementary particle, with the physical radius of your state. We know, say, for example, hydrogen, right? The radius of hydrogen is independent of the mass of the proton, which is what dominates its mass, right? The radius of hydrogen is set by the Bohr radius. That's 1 over m electron. So you can have dark matter as some hydrogen-like state, very heavy, annihilating with a much larger cross-section. To give another example, as a very crude model of a composite particle, we'll take a billiard ball. What's the scattering cross-section of 2 billiard balls? Right? It's a geometric cross-section. And this is known in systems much closer to the potential dark matter models than billiard balls. If you scatter hydrogen off anti-hydrogen, you get a cross-section that goes like the hydrogen radius. It goes like inverse m electron rather than inverse m proton. So with this proof of concept in hand, a couple of years ago with my Veritas colleagues, we projected some limits for how Veritas could bound very heavy dark matter. That was this blue curve here. Here's the projection. We see that, again, CTA will do substantially better. Hawkbush is a different kind of telescope. It actually uses a water tank to trigger Cherenkov radiation instead of the atmosphere. Also sets very large limits. That was our projection. And then we follow that up with an actual experimental analysis. So if the dark matter is annihilating to some standard model state near its unitarity limit, we can bound its physical size given a particular mass. Okay? So just want to point out, since I grew up in the LHC era where 13 TeV was a large energy scale, right? This is almost 2,000 times larger, and it was done last year. So this physics is being done already. So where do we go from here? So one conclusion I hope you can take away from this talk is that the simplest, most economical models of dark matter we have, these electroweak WIMP scenarios, they're all still presently viable, but the WINO is under tremendous experimental pressure, and the rest of them, maybe except for the 13, right, are going to be ruled on in the next decade. Of course, it behooves us to finish our current Veritas analysis, but since everyone is getting similar results, it may make sense for the different telescopes to join forces. There is a precedent for this, which for whatever reason, the Europeans called Glory Duck, where we could combine all of our similar limits. And if you just do the naive combination of everyone's limit, you get something very close to exclusion for the WINO. So that result should happen. And I'm already in discussions with people on MAGIC to make it happen. My colleague, John Quinn at Veritas, is particularly excited about a new possible dwarf galaxy called Ursa Major 3. he has preliminary limits where something like 20 hours of Ursa Major 3 data beat by an order of magnitude the 600 hours of the existing dwarf spheroidal set. It would be wonderful to fold that in. Veritas is also running for 4 more years. There's still more we can do. Again, I think dwarf spheroidals with the current telescopes are going to be sufficient for the triplet. Once you've been given permission to think about exotic representations of SU2 by dark matter, you can go a different direction, which I'm doing with my PhD student Panos Christeos and some colleagues at Penn. It's very difficult because of its unification properties to realize representations larger than 3 in string theory. So we are looking at LHC data to see, could there be some lower mass, it wouldn't be dark matter, but some lower mass quintuplet or higher representation. If that were discovered, that would place real pressure on string theory, which is famously resisted experimental tests, and yet we're doing one. I also think going forward, there's going to be more to do on ultra heavy dark matter. I think these heuristic billiard ball geometric scaling arguments are very compelling. But with some lattice colleagues at Fermilab and my friend at Carleton, Dan Stolarski, we're trying to do an honest first principles calculation of a QCD system that shows that you have geometric scattering for heavy light composite bound states. Also, if you want to explain why this ultra heavy dark matter is there, why it's so heavy, why it's talking to the standard model at all, I think there's a large model building challenge there as well. So to wrap up, dark matter has kept me very busy for much of the last decade. And I think the next decade promises to be equally, if not more, exciting. Thank you.